All right, this is NCCER Electrical 4 Revision 10 HVAC Controls Module. This is module number 26408-20. Section 1, HVAC operating principles and major components. Definitely need to read through the trade terms, especially if you're taking just electrical. You should read through this. If you're taking electrical and instrumentation with me, these systems should make a little bit more sense to you. Like having these are almost like loops in instrumentation. But you need to know the major components of an HVAC system: compressor, condenser, evaporator, expansion device. You need to know what heat transfer is, mechanical refrigeration, all of these are going to be very, very important in trying to talk about and understand how these components work together. 110 heating and ventilation system. The second sentence at the end of the paragraph is highlighted. Today, a central heating source, such as a furnace or boiler, does the job using the principle of heat transfer. That is, heat created in one place and carried to another place by means of air or water. So that is heat transfer. You are transferring heat by means of air or water. My next highlight is the last paragraph on the page. Whole thing, a couple different questions that come out of that one paragraph. Water is used as the heat exchange medium as well. The water is heated in a boiler, so a boiler uses water for its heat exchange medium. The water is heated in a boiler, then pumped into pipes in the heat exchangers, where the heat it contains is transferred to the surrounding air. The heat exchangers are usually baseboard heating elements located in the space to be heated. This type of system is known as a hydronic heating system. Hydronic means that it uses water. Flip the page. They show you a couple different examples of forced air heating. So up here on the board, you've got, this is what the box, if you've got central heat and air in your house, this is usually what the box in your attic looks like for your furnace. You've got your heat exchanger. Actually, this is your furnace or your AC. So heat exchanger, burner section, secondary heat exchanger, condensate pump, exhaust fan, exhaust vent pipe, gas valve, combustion air intake. You should be familiar with all of those and how they work together. You can see the couple different pictures they show you on page 2 for how like duct works and stuff going in different rooms and whatnot. On page, first 2 sentences on page 3 are highlighted. Natural gas and fuel oil are the most widely used heating fossil fuels. Of these two, natural gas is the most common. No surprise here, natural gas is very common. I've got natural gas in my house here in southeast Louisiana. They've also figured out a way to liquefy natural gas, and they're going to, that's the multi-billion dollar plant, Venture Global, that they're building down the river. Natural gas is the most common type of fossil fuel we have today. Page 4 and 5. They go into air conditioning. They talk about, you should definitely read through where it says mechanical refrigeration and what refrigerant is and how they work together. I don't have any highlights on page 4, but there's a bunch of stuff that it goes into. All the way at the bottom, page 4, evaporator, condenser, compressor, expansion device. All of those are covered on page 5. Matter of fact, most of those are highlighted. So on page 5, the system components, I've got the evaporator highlighted. The evaporator is a heat exchanger where the heat from the area of the item being cooled is transferred to the refrigerant. So this is the coil inside your attic. Your house heats up the oil inside that evaporator, and then that moves that oil outside to be cooled off. You've got the compressor, don't have it highlighted, but you should read through that. Condenser, a heat exchanger where the heat is absorbed by the refrigerant, is transferred to the cooler air, outdoor air, or another substance such as water. So this is your outdoor condenser unit. Expansion valve, expansion device. This is also a highlighted device that provides a pressure drop that lowers the boiling point of the refrigerant just before it enters the evaporator. This is known as a metering device. Expansion device is a metering device. So, also along with these devices, that you're going to have the pathway for the refrigeration components to flow. Those are the next bullet points on page 5. I have the suction line highlighted. The suction line is the tubing that carries the heat-laden refrigerant gas from the evaporator, which is inside, to the compressor, which is outside. Going through the refrigeration cycle, they have a cycle that it has to go through that works with the thermostat. This is where instrumentation students should be more familiar with systems and closed loop systems and how they work, and that's basically how a thermostat works. But in refrigeration cycle, on the right hand side of page 5, the second to last paragraph, last sentence is highlighted. So it is a low temperature, low pressure refrigerant vapor that travels through the suction line to the compressor. So leaving the evaporator. That whole paragraph, you should read through that whole paragraph because it talks about how the evaporator works. So the first sentence, it says the evaporator receives a low temperature, low pressure liquid refrigerant. And then the output is the last sentence. So the low temperature, low pressure refrigerant vapor. So it goes from a liquid to a vapor. And it travels through the suction line back to the compressor. So it is a vapor that is going out, liquid that's coming in, and vapor that's going outside. You can see the refrigeration cycle, whether it's an outdoor unit or anything like that. They either up here on the board on the bottom, or you got that figure 4 on page 6. So that's all I've got for. Wouldn't be a bad thing to read through the heat pumps on page 8, but that's all I've got for these two sections. So 1, 2, 3 talks about heat pumps, and then you'll want to go to the section 1 review on page 9. You got a couple questions in there, and make sure you're answering these section review questions because this is HVAC stuff is similar to electrical, but it's a lot more. There's a lot of stuff going on, and there's only one chapter in all 4 levels of electrical that cover this stuff. So you want to make sure you know it because even if you're out working in a plant or something like that, I've worked in the steel mill that I worked in. All mills will have a control room that has to be air conditioned, and air conditioners go out. And whenever air conditioners would go out for us, we had a 24-hour line we called and would call. They'd come out, turn it back on, but maybe the person on call wouldn't be answering, or something happened where he couldn't come in, or something like that, or even if he said I live an hour away. And once these PLCs and stuff like that get so hot, they shut themselves down. There's safety's inside of them, so you can shut a plant down if these get too hot. So that's if it's something simple like a thermostat or something like that. Like it is important to know this stuff and know how it works, even if it isn't your exact area of expertise. So, continuing on to section 2. You're going to have thermostats. You're going to have different types of thermostats. They talk quite a bit about older types of thermostats. Most everything is going to electronic thermostat. Nothing's going to have mercury in it anymore, or at least very, very few. A lot of stuff is changed out by now. But you should know some of these trade terms. I'll talk a little bit about the automatic changeover thermostat, bimetal thermostat, the deadband, the differential, in-bar substance used, and then definitely what a thermostat is. A thermostat is just the unit that controls your HVAC equipment. So in 210, I need to go to the next section. Earn it. So, thermostats, 210, operating principles, second paragraph, first 2 sentences are highlighted. A bimetal element is composed of 2 different metals bonded together. One metal is usually copper or brass, and the other metal is called Invar, which contains 36% nickel. So you can see these two pieces of metal are right next to each other. They expand and contract at different rates, which we can do an engineered calculation for how much they'll move and base a temperature based on that engineered calculation. That's how they get a bimetal element to work. That's the old school way of thermostats. The warning on page 10 also has a highlight in it. Second to last sentence: do not dispose of thermostats containing mercury bulbs in regular trash. Mercury is very poisonous, causes you to go crazy. That's why the Mad use mercury in making hats and stuff like that. That's why in Alice in Wonderland the Mad Hatter was crazy, because of mercury inside of his hat. But yeah, if you find these, don't throw them away. You want to find some type of electronic waste or something like that and get them thrown away where they're supposed to go if they have that mercury inside them. Page 11, first paragraph on the page, first two sentences are highlighted. Most residential and small commercial thermostats are of the low voltage, the 24 volt type. With low voltage control circuits, there's less of a risk of electrical shock and less of a chance of fire from short circuits. So there's usually in the unit itself, in the attic or something like that, there's a transformer that takes usually 120 or 240 in and transforms that down to 24 volt, and that's what goes to your components in your thermostat and stuff, so you don't have higher voltage in your thermostats. 211 heating only thermostat. So this is where it would get super cold, like up in New York and stuff like that, where they don't even have air conditioning. Or some people don't have air conditioning and stuff like that. They might have heat only, and that's where they use boilers and stuff like that more often to get heat, because it gets super cold but not super hot. So heat only thermostats, they use the boiler, and once the system for that is very, very slow. A lot of us down here in the South don't even know how those systems work, but in like big buildings and stuff like that, it's way more efficient to have a boiler unit and run heating, base for heat and stuff like that around your house than it is to use electric heat and whatnot. It just doesn't keep up. But the bad part about this is it's very, 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 very slow reacting to temperature-wise. So if you want a certain temperature in your house, you can say get up to 70 degrees. Well, it gets up to 70 degrees and it cuts off the heat to the boiler, but that doesn't mean that the air or the water inside this boiler and stuff is cool. So it is still putting hot water through, so it actually get a little uncomfortably hot in the room. So to avoid this, second paragraph, second and third to last sentence, to avoid occupant discomfort, this is in 211, an adjustable heat anticipator opens the thermostat before the temperature in the space reaches the set point. The heat anticipator is a small resistance heater in series with the switch contacts. So let's just say it shuts off before it gets to the set point, and that way it doesn't get too hot in the room or in the conditioned area. You'll have pages 12 and 13. You'll have 212 cooling only thermostats. Usually, I've never seen that. That would be in like super hot areas where you would only have air conditioning, but usually if you have air conditioning, you have heat, but there's no highlights in that. I don't have any highlights on page 12. Most of the time you have heating, cooling thermostats, which is 213, so you're just switching it to heat or cool. That's what most of us have in our house. 214, automatic changeover thermostats. This is where I said you should read through the trade term, which is on page 13. But for these automatic changeover thermostats, 214, second paragraph on page 13, the first sentence is highlighted. The thermostat contains a built-in mechanical differential, which is the difference between the cut-in and cut-out points of the thermostat. So this is where the thermostat will shut on and shut off. Just read that's the highlight that I have, but the rest of the paragraph explains it. The differential is normally 2 degrees. For example, if the heat set point is 70, the furnace will turn it on at 70 degrees and run until the temperature is 72. So it's like for instrumentation students, it's like a buffer zone or a neutral zone that's put in an instrumentation loop. Next paragraph, first two sentences are also highlighted. Automatic changeover thermostats also have a minimum interlock setting commonly known as the deadband. The deadband is a built-in feature that prevents the heating and cooling set points from being too close to each other. You don't want your unit to switch back and forth between cooling and heating. Very, very, very inefficient. So this is a system that's built into these automatic changeover thermostats. Most of your heating, cooling thermostat, digital thermostats have the ability to do this. I have it in my house. I just never, we still have a little bit of seasons and stuff like that, so we shut off our air conditioning completely. But this would just be like if I just wanted to set my house to 70 degrees and never touch my thermostat ever again, I could set this type of thermostat up, and it would keep it at 70, whether it was the winter or the summer or anything like that. 215, multi-stage thermostats. This is, you're getting more into commercialized buildings once you start talking about multi-stage thermostats. 215, third paragraph, it's the sentence, couple sentences that split the columns, but starting with the third paragraph in the bottom left of page 13. Heat pump thermostats usually have an emergency heat switch. If the heat pump compressor becomes inoperative, this switch locks out the normal heat pump operation and heats the area with auxiliary heat or other connected heat source until the problem can be corrected. So this is just for heat pumps. We don't have a lot of heat pumps here, or not that I've seen, because mostly because we have natural gas. But back where I'm from in Tennessee originally, a lot of heat pumps. And heat pumps, we'll talk about heat pumps and how they work and stuff like that. But if a heat pump can't keep up, it will turn on an auxiliary heat source, so like some resistance type heaters, to get some heat in the house so it doesn't get too cold. Programmable thermostats, that's what like Nest thermostats, stuff like that, like my thermostat can sense where I am, so whenever I'm heading home, it can say turn on the air conditioning so it's not 78 degrees in the house. I turn it down before I get there. So you can have a lot of, are programmable to the point of timing and stuff like that. Like whenever 10 o'clock at night, I think my thermostat goes, in the summer and stuff, it'll turn itself down to like 71, 72, where I'm not reset or setting the thermostat or anything like that. It's programmable. No highlights in that. Page 14 and 15, I don't have any highlights in these. In the thermostat installation, like you will, there will be some installation highlights, but they do, starting in 221, they have some guidelines, and those continue over to page 16. On page 16, the first paragraph on page 16, third sentence is highlighted. Locate the thermostat in wall plane or sub base about 5 feet above the finished floor in an area with good circulation at room temperature. So this is on an interior wall. Usually you're hanging this on an interior wall, but the important thing is 5 feet from above the finished floor with good air circulation. A lot of times this is in your hallways and wherever your return is. That's just where it is most of the time. Thermostat wiring, 222. There are four questions on that thermostat wiring code. This one right here. You need to know what these different colors and terminal designations are. R is red for power, G is green, which is for fan control, Y is yellow, which is for your cooling control, W is white for your heating control, O is orange. You only use that for a heat pump. So you wire up 4 or 5 wires in the thermostat. Thermostat wiring at the bottom is also covered, so you should know how to read through that by now. They go through adjusting heat anticipators, so that's for those heat-only systems. Cycle rate settings, final check. I don't have anything else highlighted on 17 and 18, so you'll have 2 questions on page 18, and I'm going to continue on to section 3. Section 3, HVAC control systems. Trade terms, you've only got one, analog to digital converter, ADC. It's used in this section. 310, 311 are comfort cooling controls, motor speed controls. So some of these actually can control the motors like that. These are for the more high-tech units. It is more efficient to control the motor speed rather than just control on or off. No highlights in that. Going on to page 20, lockout control circuit, 312. First sentence of 312 is highlighted. The purpose of the lockout relay in a control circuit is to prevent the automatic restart of the HVAC system after a safety device has shut it down. So, if a safety device has shut down the HVAC system, you cannot start it back up until you figure out what was wrong and reset that. Right-hand side of page 20, that second to last paragraph, the whole thing is highlighted. If the lockout relay becomes defective, it should be replaced with an exact duplicate to maintain the proper resistance balance. This type of relay is sometimes called an impedance relay. To page 21, time delay relays. So you're going to have different types of time delay relays that make stuff happen at different times. The highlight that I have, all of this you should read through the sequencing of how heating and cooling systems work. All of these sections are going to be good to read all the way through. But my highlight is the third paragraph, first sentence. A sequencer is a special type of time delay relay used to energize resistance heaters in heat pump, air handler, or electric furnaces. So this is a timer that will turn on resistance heater in a heat pump. 314, compressor short cycle timer. If any of you have like a Nest thermostat at the house and you've ever gone to the thermostat to try to turn it on and it's got a timer going, that means that like you've turned it on, turned it off, and trying to turn it back on, it's not going to start back up because it wants the pressure to go back down because it doesn't want that compressor starting up against a higher pressure. But second paragraph, first sentence is highlighted in 314. A compressor short cycle protection circuit contains a timing function that prevents the compressor contactor from re-energizing for a specified period of time after the compressor shuts off. It's usually about 30 seconds up to 5 minutes. I think the one at my house is 2 minutes, but it just gives time for that pressure to be relieved off of the suction side. Control safety switches. Control circuit safety switches. So these are different things. Switch that will shut down the unit so it doesn't damage itself. And if you go on to page 22, you can have freeze protection. So you have a freeze stat, which is what's on the board or the top left of your page 23. I've got the first paragraph on page 22 highlighted. Freeze stat, another type of safety switch, is the freeze protection thermostat, FPT, commonly called freeze stat. Its purpose to prevent the evaporator coil freeze up. The freeze stat switch, figure 24, is a normally closed switch. Key in on that. That is usually attached to one of the end valves in the evaporator coil. It will open if the refrigerant temperature drops below a predetermined set point. So this keeps the evaporator coil from freezing up. You've got different types of furnace controls. 320. You've got high temperature limit switch. This is just a switch that if it gets, they show that in the circuit. Okay, if the furnace gets too hot, this can be caused by a blocking the ventilation and stuff like that, the switch will open up the circuit, it'll shut off the gas valve and shut down the unit and let people know, or let somebody know that something's wrong. The rollout switch, the first sentence of 322 I've got highlighted. Another type of limit switch known as a rollout switch, figure 26, is also mounted near the heat exchanger just outside the burner section in the vestibule to stop the burner if excessive temperature is reached. So this is another one, if it gets too hot, we'll shut the burner off. Moving on from there, going on to 24, the inducer proving switch, 324. You need to read through this section. You need to know the sequence of operations in HVAC heating circuit. Certain steps, stuff turns on in certain ways, and certain safeties are in there to make sure that stuff turns on before going on to the next part of the sequence. But on page 24, 324, the inducer proving switch, the whole first paragraph is highlighted. Modern gas furnaces use an inducer motor to induce or produce a draft. These furnaces have either a centrifugal switch or a pressure operated switch in the heating control circuit to monitor the operation of the inducer motor and verify that it is running. If the inducer motor fails to operate, the switch opens and prevents control voltage from being applied to the gas furnace valve, or the furnace gas valve. So this is just making sure the inducer blower motor is running. So you either have a pressure operated switch or a centrifugal switch. Most of the time it's going to be a pressure operated switch, which you can see pressure switch right there on the board. So that's, don't really show the air hookup, but it's all the way at the bottom, but that just is what the next step is from turning on the gas valve. The heat pump defrost control, so completely separate section, heat pumps. So how heat pumps work, they work the direct opposite of an air conditioning unit. Pause this for a second. Alright, sorry about that. But heat pumps work directly the opposite of air conditioning systems. So they heat up the oil outside, or the refrigerant outside, bring it inside, and then that hot refrigerant is used to go through the coil, and then the air blows through that, which heats up the house. But my highlight, I got the first, I guess that's first paragraph all the way through the last sentence in the bottom left of 24 is my first highlight. When heat is transferred from cold outdoor air to the refrigerant in the outdoor coil, moisture condenses on the coil. Because of the temperature of the outdoor coil surface, this moisture will freeze on the coil. Over time, the frost will build up on the coil, blocking airflow and preventing effective heat transfer. This is normal and expected, and it is most likely to be a problem at temperatures between 28 degrees Fahrenheit and 40 degrees Fahrenheit than it is at lower outdoor temperatures. Colder air typically carries less moisture. To eliminate ice buildup on the outdoor coil, most heat pumps have a defrost section. So they have a defrost which comes on to make sure that outside coil does not get ice built up on it. Immediate next sentence. So out the top of this next sentence, up at the top right, I wrote defrost is accomplished by, in air-to-air heat pumps, the heating cycle is reversed, placing the unit back into the cooling mode. So it's in cooling mode, which heats up the outside unit, the ice melts off, and then it can turn back on to heating mode. Same paragraph. I've still got a couple more highlights in this same paragraph. Second to last sentence, that paragraph I have highlighted. During the defrost cycle, the unit is essentially using heat from the indoor air to melt the ice on the outdoor coil. Next sentence, separate highlight. To prevent discomfort to building occupants from cold air blowing during the defrost cycle, a supplemental electric heater is usually energized to rewarm the air before it enters the room. So these can have little bitty electric heaters that will warm up the air before it goes into the room while the heat pump is in defrost mode. Moving on from there, going into HVAC digital control systems. These would be like all the systems that are controlling big, large industrial HVAC systems, like the one in this building back in Nunez. Nothing highlighted in the first 340 section, but if you flip over to page 27, 341 controlling devices. First paragraph, top right of page 27. That second full sentence in the top right of 27 through the end of the paragraph is highlighted. The first group includes external digital devices. These might be relays, switches, lights, and other devices that can be operated in either a full on or full off or binary condition. So digital devices used with these HVAC systems, relays, switches, lights, only stuff that can be on or off. The next paragraph is the kind of the opposite, but it's a separate highlight. First two sentences. The second group includes external analog devices. Devices in this group include thermistors, photocells, and DC motor controls. So these are going to be external analog devices. Digital control system examples. So these are going to be different types of control. So chillers, stuff like that, stuff that you might work on in bigger industrial systems. 342 on page 28, first paragraph, last sentence is highlighted. In a variable air volume system, a single unit can serve several zones. So I'm pretty sure that's how this building back here works. We have a thermostat in this room. I can lightly control the temperature of this room, whereas back in the unit outside, like there's a wide band or a wider band that we're going to control. Say it'll control those anywhere between 70 and 80, and then I can control my room anywhere between 70 and 80. Like 7, if that makes sense. It'll control it 270 to 80, and then I can control in between 70 and 80. Control circuit operating sequence. So this is just how stuff works for the HVAC or the air conditioning side of the house. We talked about the sequence a little bit for the heating side. This is for the air conditioning side. So page 29, top right, it says figure 20 or figure 36, which is this one right here on the board. Is more typical of a basic cooling system and has features that are common to most cooling system circuits. So it shows how this works. So this would just be for cooling. So it says to come on. If I have this switch down in auto, the thermostat or temperature control comes on, turns on my compressor contactor as well as my inducer motor or IFR relay. So I can see IFR, my inducer motor will come on, and then for my C coil, that will turn on my compressor motor as well as my outside fan. But it talks about that in the bullet points where it's going through those 4 bullet points. My highlight is the third bullet point, first sentence. The outdoor fan motor, OFM, runs whenever the compressor is on. That is if that compressor is running, that outside fan motor is running. The next paragraph after the bullet points, I have the whole thing marked to read through, and then I keyed in on the second to last sentence. So I'm going to read through the whole thing and then keying in on the second to last sentence. No matter how complex the control circuit appears to be, you will find the basic control arrangement shown in figure 36 or something very much like it at the heart of the circuit. Everything else will be special features to improve equipment safety or operating efficiency. This is illustrated in figure 37. This diagram is for a combined cooling and gas heating unit. The circuit looks different and there are several more components. However, if you trace the cooling control function, you will see that it is essentially the same as that previously shown. The differences are that the heating controls have been added near the bottom of the diagram, along with the heating cooling thermostat. Key in on this sentence. The cooling component has more extras, such as a compressor short cycle protection circuit a crankcase heater, and a current-sensitive overload device. Take away these components and you have a circuit that is identical to the one in Figure 36. So that's just comparing these two different ones. This is just cooling. This is adding a natural gas heating element to that. Page 31, you're going to need to know how to read through this. And whether that's asking me in person to run through this or actually reading through, you're going to need to know how to read through this. So if I'm looking down here, I have my legend down here at the bottom, and I'm looking for my thermostat. Excuse me. This is my thermostat right here on the left. So you can see if this is switched on, it has off, cool, and heat. So you need to read through these. If I have it switched down to heat, I can see that I have a temperature that has to be met. I've got a I guess this is just the switch. This is the HA is say a variable resistor. But key in that after it comes out. Wait a second. I meant switch to cool. The question that you're going to have is coming off the cooling cycle. So if this is switched to cool, you got your temperature switch right here, and then my yellow wire goes into my short cycle T1. I'm still wrong on that. You should just know how to read through this schematic because you're going to have a question based on that. You're going to have a question in the heat mode. So it's going to say what happens as soon as I turn it to heat mode, and the thermostat's calling for heat. So if it's calling for heat all the way to right here, you're going to get your wire going to the IDR. I look down here on what IDR, and that's my induced draft relay. So my relay going to my IDR contact up here. IDR is going to turn on my IDM. If I look at what my IDM is, that's my induced draft motor. That's my inducer motor. So that's the first thing that's going to happen when I turn my thermostat to heat. That's something you should know. You should know how to read through that. And those are the I would read through that section on how to read through that schematic for sure. If it doesn't already make sense. By this point, you should know how to read that in electrical 4. Troubleshooting, page 32, second warning on the page. The last two sentences are highlighted. The capacitors used in motor circuits can hold a high voltage charge after the system power is turned off. Always discharge capacitors before touching them. So capacitors hold a charge. Make sure you're discharging them if you're pulling them out or messing with that stuff. You have the HVAC troubleshooting tables on pages 34 through 37. You are going to have a question that from this section review coming off of that in table 1A. Make sure to reference the table when looking for that. And then that's all I've got for this section. You've got the 6 questions on page 38 to go through, and I'm going to continue right on into the next section, section 4, which is the last section. So section 4 has to do with the NEC requirements. You should know how to look through the NEC at this point. I'm just going to give you the bullet points on what to look for in this stuff. 410, last sentence, part of the sentence is highlighted. I've just got NEC Article 440, Part 5 5 covers requirements for motor compressor controllers. That's 440 Part 5 is for motor compressor controllers. NEC requirements for HVAC equipment. If you're looking at this picture that's on the board or on page 40, I've got that first one all the way in the top left highlighted. It's got 440.14. Disconnecting means shall be located within sight and of a readily accessible from the air conditioning or refrigerating equipment. That is NEC section 440.14. That's why you have a disconnect right by your air conditioner outside your house. Compressors. Page 41, 421, third paragraph, first sentence. Where refrigeration compressors are driven by conventional motors or non-hermetic, the motors and controls are subject to Article 430. Room air conditioners. 422 talks about what a room air conditioner is, but you just need to know, I highlighted the whole first paragraph, but you need to know that for a room air conditioner, that comes from Article 440, Part 7. So that paragraph is highlighted, but room air conditioners are covered in Article 440, Part 7. Second to last paragraph on the page, last sentence is highlighted. The rating of a cord and plug connected room air conditioner must not exceed 50% of the branch circuit rating if the lighting units and other appliances are also supplied. So regular plug at your house, you have to make sure you're not taking up more than 50% of the rated voltamperage or wattage of that circuit. Page 42, you're going to have a question come out of table 3. You're going to have a module review question come out of table 3. That's about all I'm going to tell you. Page 43, more NEC regulations governing motor compressors. Same thing, top right of the page. The 440.33 one is highlighted. Motor compressor with additional motor loads shall have an capacity of not less than the sum of the rated loads plus 25% of the largest motor's full load amperage. That comes from NEC section 440.33. You need to know that one. Electric space heating cable 424. The second sentence is highlighting a 120 volt cable connected to a 240 volt circuit will melt the cable. Cannot connect. That's why for a 240 volt plug, the hot side is horizontal. You should not be able to plug a 120 volt plug into a 240 volt circuit. They got compressor branch circuit controls, lighting and switches for HVAC equipment. You got to have a light inside your attic. Got to have a plug inside your attic. That stuff's marked on page 45 and figure 41. Same thing for 46 and 47. They've just got all the different places where you're going to use these NEC sections. I've got none of those highlighted all the way through page 48. Got 2 questions on page 48, section review on page 49, and of course your practice test. That is all I have for this chapter.